In this lecture, we will be studying the following three notions. First, we will talk about symmetric bilinear forms. Secondly, we will discuss quadratic forms. And the third notion that we will be discussing is symmetric matrices. We're going to see that these notions are largely interchangeable, and they will form our toolbox. That is, when studying one of these constructions, we will also be invoking another. For example, we will be using eigenvalue properties of symmetric matrices when studying quadratic forms. And we will be using quadratic forms to define positivity for symmetric matrices. We will begin with the definition of a symmetric bilinear form. Let V be a vector space over a field F. A symmetric bilinear form is a function from the Cartesian product V cross V to the field. So this means that the bilinear form is a function of two arguments. Each argument belongs to our vector space, and we will denote bilinear forms by round brackets. And so here we put arguments inside these parentheses. And we will require that these functions will satisfy certain axioms. So first of all, it's symmetric. So that is for all u and v in the vector space V, the value of this bilinear form on uv is the same as the value on v and u. And it's bilinear, which is a set of four familiar axioms. First, the value of u with v1 plus v2 is equal to u with v1 plus u with v2. Then, actually, by symmetry, we also conclude that this is true for the first argument. u1 plus u2 with v is equal to u1 with v plus u2 with v. 3. If we put a constant multiple of one of the vectors, then this constant multiple can be pulled out from the bilinear form. So here C belongs to the field. And 4, finally, the same is true for the first argument. C times u with v is equal to C times u with v. Symmetric bilinear forms generalize the notion of the dot product, and they are known under various names in mathematics. So other names for the symmetric bilinear forms are inner products or scalar product. Suppose vector space V is finite dimensional. And let B be V1 through Vn be a basis of vector space V. the matrix of the symmetric bilinear form relative to basis B is the matrix A, or sometimes we will denote it as A, B, so to indicate that this is relative to basis B, with the entries Aij defined as the values of the symmetric bilinear form on the basis vector, so Vi with Vj. Since our bilinear form is symmetric, and in particular the value of Vj Vi is equal to the value of Vi Vj, so this implies that its matrix is also symmetric. So that is Aj is equal to Aij, or this can be also expressed as A transpose is equal to A. Let us show that the bilinear form may be recovered from its matrix. Suppose we take two arbitrary vectors, u and v, in this vector space. So let us expand them as linear combinations of basis vectors. U is equal to x1 v1 plus xn vn, and v as y1 v1 plus yn vn. And here the column vectors x1, x2, xn. So this is the vector of coordinates of a vector u relative to the basis b, and the vector y1, y2, yn is the coordinate vector of v with respect to b. Now let us evaluate the form u and v. So this is, so for u we put the sum k goes from 1 to n, xk, vk, and for v we put its expansion, the sum s goes from 1 to n, ys, vs. And then using bilinearity properties, so this becomes the double sum in k and s from 1 to n, xk, ys, times the value of the bilinear form on the basis vectors, vk, vs. But this is exactly the AKS value of the matrix. So what we get is we get the sum k and s from 1 to n. We get AKS times xk, ys. If we rewrite this formula as the scalar product of u with v is the sum ks from 1 to n, and we write it as xk aks times ys, then this form shows that we can rewrite this using the matrix product. So here we will get that the value of bilinear form on u and v is the product of, so we take coordinate vector ub and take its transpose, so turn it into a row, times matrix A in basis B, times the coordinate vector of v with respect to basis B. If we fix a basis in a finite dimensional vector space V, then we see that any symmetric bilinear form will yield a symmetric matrix just by evaluating this bilinear form on the basis vectors. But we also see that this correspondence goes the other way around. That if we have a symmetric matrix, then we can define a new symmetric bilinear form using this matrix with this formula. Let us state this as a lemma. Let A be a symmetric n by n matrix with entries in the field F. Then the following expression. So U V is equal to U transpose times A times V defines a symmetric bilinear form on vector space Fn. Here we will need to verify that this satisfies all axioms of a symmetric bilinear form, and I leave the proof of this lemma for you as an exercise. We make a remark that the dot product on Fn is a symmetric bilinear form whose matrix in the standard basis is just the identity matrix. In our discussions, we will often consider symmetric bilinear forms given in addition to the standard dot product on the space Rn. So that is, we will be studying two bilinear forms at the same time. One which is the standard dot product and another which is a given bilinear form. A quadratic form Q on the vector space Fn is a function Q from Fn to F given by a polynomial expression that Q applied to a vector x1, x2, xn. This is the sum where k is less or equal to s, and these are going from 1 to n, rks times xk times xs. In particular, quadratic forms have the following property. That for every c in the field, q of c times vector v is equal to c squared times q of v. Let us write down an example of a quadratic form q on a three-dimensional space F3 with q of x, y, z defined as x squared plus 4xy plus 3y squared minus 6yz plus xz and minus 2z squared. Let us point out a connection between bilinear and quadratic forms. So if we have a bilinear form on Fn, then this gives us a quadratic form. On Fn. We define Q evaluated on a vector u as the bilinear form of u with u. And if we write u as a column vector x1, x2, xn, then Q of this vector x1, x2, xn will be given by the row x1, x2, xn times matrix A of this bilinear form times the column x1, x2, xn. Or this can be written as a sum. So this is the sum where k and s go from 1 to n. And here we will have aks times xk times xs. And we see that indeed this expression gives us a quadratic form. Let us write down the matrix that corresponds to this quadratic form. So here we'll get a 3 by 3 matrix. The diagonal entries correspond to terms x squared, y squared, and z squared. So here we'll have 1, 3, and -2. So for off-diagonal entries, so we see that the term x times y will appear in this formula twice, when k is equal to 1 and s is equal to 2, or when k is equal to 2 and s is equal to 1. For this reason, when we put this term into a matrix, we should divide the coefficient by 2. So here we'll have 2 and 2 here, and the same for the term minus 6yz. So this becomes a coefficient -3 here and -3 here. And for the term xz, we will have to put coefficient 1/2 here and the coefficient 1/2 here. And then we can easily see that this expression in terms of matrix product can be written as a row xyz times matrix A times the column xyz. So we see that from the coefficients of the quadratic form, we can read out the symmetric matrix. So this suggests that we can go back from quadratic forms and recover the bilinear forms. Let us state the following lemma. Suppose the characteristic of the field is different from 2, and let Q be a quadratic form on a vector space V that comes from a symmetric bilinear form on V. So that is, we define Q of U as the bilinear form evaluated on U and U. Then the bilinear form may be recovered from the quadratic form using the following formula, that UV is 1/2 of Q of U plus V minus Q of U and minus Q of V. We impose the restriction that the characteristic of the field is different from 2 because we need to divide by 2 in this formula. The proof of this lemma is a direct verification. So let us evaluate the right-hand side. So here we have 1/2 and Q of u plus v is the bilinear form of u plus v with u plus v minus, so the bilinear form uu, and minus the bilinear form vv. And when we expand this using bilinearity, so we see that the terms uu and vv will cancel, and we just get 1/2 of uv plus vu. And because the form is symmetric, these two terms are equal, and we simply get the bilinear form uv. And this shows that we can recover the value of bilinear form on arbitrary pair of vectors from the values of the quadratic form. Now we see that we have three notions of symmetric bilinear forms, quadratic forms, and symmetric matrices. And these three notions are interconnected and interchangeable. So this means that we can go from one object to another. This will help us to develop the theory because certain properties are easier to express in one language and other properties are easier to study using a different object. From now on, we'll take the field to be real numbers and the vector space to be Rn. Let us give a definition. A quadratic form on Rn is called positive definite if for all vectors v different from 0, we have q of v is greater than 0. We see that in terms of bilinear forms, the corresponding analog will be, so we say that a bilinear form is positive definite. If for every vector v in Rn, v different from 0, we have the value of the bilinear form is positive. Now let us consider an example. Are the following forms on R2 positive definite? And in the first case, we take the form, so q of xy is x squared minus 4xy plus 5y squared. And in the second case, let's take q of xy to be x squared minus 4xy plus 3y squared. Is it true that we generate positive values when we plug in arbitrary non-zero values for x and y? I suggest that you pause the video here and try to answer these questions. The first form can be written in the following way. So we can write it as x squared minus 4xy plus 4y squared and plus another y squared, right? So we are doing the completion of a square here. So this is x minus 2y squared plus y squared. And because we succeeded in writing this form as a sum of two squares, so we can easily see that this is positive definite. For the second form, if we try to do the same trick, the result will be x squared minus 4xy plus 4y squared minus y squared. And so this becomes x minus 2y squared minus y squared. And we see that this is not positive definite. So, for example, if we set x to be equal to 2y and y be non-zero, then the value of this quadratic form will become negative. This brings us to the following question. So, how to determine whether a given quadratic or a bilinear form is positive definite. Or more generally, we may ask how to compute the following. So what will be the maximum over unit vectors? So we take vectors of length 1 in Rn of the value of the quadratic form on vector u. And likewise for the minimum. So that is, we take unit sphere in vector space Rn and the given quadratic form, and we want to find the maximum value of the quadratic form on the unit sphere and the minimum value of the quadratic form on the unit sphere. So here the unit sphere is of course defined relative to the standard dot product. In particular, we may ask this for this quadratic form. So what is the maximum when x squared plus y squared is equal to 1 of the expression x squared minus 4xy plus 5y squared? And what is the minimum of this expression on this set? Let us state one basic but an important result about positive definite symmetric bilinear forms. So this is called Cauchy-Schwarz inequality. Let V be a real vector space with a positive definite symmetric bilinear form. Then, for all u and v in this vector space, we have that the absolute value of the bilinear form on u and v does not exceed the square root of the bilinear form squares of u with u and v with v. Let us give the proof of this inequality. Consider a new vector w, which is u minus t times v, where t is a real number that we are going to fix a little later. Here we are assuming that both vectors u and v are non-zero, because if one of these vectors is 0, then we get 0 in both sides. Because the form is positive definite, this implies that when we evaluate w with itself, this must be greater or equal to 0. But now, if we substitute this expression for w and expand it, then what we're going to get is that u with u minus 2 times t u with v and plus t squared v with v is greater or equal to 0. Here, t is arbitrary, and now we set it to a particular value. So we set t to be uv over vv. And we point out that we have chosen v to be a non-zero vector, so the denominator is non-zero. Then this inequality becomes uu minus 2 times uv squared over vv plus uv squared, and 1 vv in denominator will cancel over vv, is greater or equal to 0. Now, multiplying by the positive value vv and simplifying, we get that uu times vv is greater or equal to uv squared. And now, extracting the square root of both sides, we get that the absolute value of the bilinear form evaluated on u and v is less or equal than the square root of the product of u with u times v with v, which is exactly the Cauchy-Schwarz inequality. Next, we are going to discuss the change of basis for matrices of bilinear forms. We consider a Euclidean space Rn with a symmetric bilinear form that we denote by round brackets. So this means that on Rn we have the dot product, and in addition to the dot product we also have one more symmetric bilinear form. Let us recall our construction of the matrix of this bilinear form relative to some basis b. Such a matrix will allow us to compute the values of the bilinear form using the coordinates of vectors relative to the basis b. So this means that for any two vectors u and v in Rn, so the value of the bilinear form is given by the coordinate vector of u relative to the basis b transpose. So we take the coordinate vector and convert it into a row. Then we have the matrix of the bilinear form relative to the basis b, ab, and then we have the coordinate of vector of v relative to basis b. For matrices of bilinear forms, we are going to write the symbol b on the top to distinguish them from matrices of linear operators. This matrix can be computed for any basis, and its entries are just values of the bilinear form evaluated on the two basis vectors vi and vj. In particular, we can compute the matrix of a bilinear form in the standard basis of Rn, and we get that for all u and v in Rn, so the same bilinear form u and v can be also expressed using coordinate vectors in the standard basis. So this will be u standard transpose times a in the standard basis times v with respect to the standard basis e of Rn. We would like to derive the relationship between these two matrices, the matrix of the bilinear form in the standard basis and the matrix of the bilinear form in a non-standard basis. Recall that we have the notion of the change of basis matrix. So we will denote this matrix as C or C B to E, and this matrix recomputes the coordinates of vectors from B basis to the standard basis. So this means that if we take this matrix and we multiply by it on the left the coordinates of any vector u with respect to basis B, then what we obtain is the standard coordinates of the same vector. We calculate the change of basis matrix in the following way. We have a standard basis in Rn, so these are given by vectors E1, which is 1, 0, 0, 0, E2, 0, 1, 0, 0, and so on. And then we have some basis B. So this matrix is formed by placing the standard coordinates of vectors from B as columns. Now let us take this relationship and substitute it in our second formula. Then we get that the value of the bilinear form on vectors u and v is equal to, so instead of ue, we are going to write the change of basis matrix times the b coordinates of vector u, and all of this has to be taken with a transpose. Then we have a in the standard basis, and we do the same trick for vector ve. So here this will be the change of basis matrix times the b coordinates of a vector v. And now we use the fact that the transpose of the product is the product of transposes in the opposite order. So this becomes ub transpose times c transpose times ae times c times vb. Recall the following lemma. If we have that u transpose a v is equal to u transpose b v for all u and v in Rn, then matrices A and B are equal. And the proof of this is quite easy, that if we set u to be the standard basis vector ei and v be the standard basis ej, then ei transpose times a times ej. So this will be equal to the entry of the matrix A, aij. And if we do the same thing for the right-hand side, then we get the entry of the matrix bij. And then we obtain that all entries of matrices A and B are the same, so these two matrices are equal. Now we're going to apply this lemma to these two equalities. And so here we see that left-hand sides are equal, so these are just values of the bilinear form on u and v. And in the right-hand sides, vectors ub and vb are arbitrary. Then we conclude that the matrix AB is equal to the product of matrices in the middle here. And now we obtain the following theorem. Let the symmetric bilinear form on Rn have matrix AB relative to basis B and matrix AE in the standard basis. And let C, which is C B to E, be the change of basis matrix. Then we have the following relationship between these two matrices. A relative to the basis B is equal to C transpose times A in the standard basis times C. And we point out that for matrices of linear operators, we have a different transformation law. For matrices of linear operators, where we will write the symbol of a basis at the bottom, the transformation law is with an inverse. So it's C inverse times A in the standard basis times C. So for linear operators, the left factor in the change of basis formula has the inverse, and for bilinear forms, instead, we have a transpose. Nonetheless, in the next lecture, we're going to see that we will be able to employ the machinery of linear operators in order to study matrices of bilinear forms. As we know, linear operators behave better over complex spaces. For this reason, we will need to extend the bilinear forms from Rn to complex spaces. This will be done not through complex bilinear forms, but rather through complex hermitian forms. We begin by discussing the construction of a complexification of a real vector space. Let V be a vector space over the field of real numbers. We define VC, the complexification of V, as a direct sum of V plus IV. Essentially, we take two copies of V, only one of these copies we decorate with the symbol I. This tells us that every vector in VC will have two parts, a real part and an imaginary part. Let's give a couple of examples. So, complexification of Rn is Cn. So, for example, if we take a complex vector 2 plus I, 3i, and minus 5 minus 4i, then this complex vector can be written with a real part and an imaginary part. So this will be 2, 0, negative 5 plus I times 1, 3, negative 4. So what we see is that C3 is R3 plus I times another copy of R3. So we have R3 as a real part of a complex vector and another copy of R3 for the imaginary part of a complex vector. As our second example, let us take F to be the space of functions from real numbers to real numbers. So these are real valued functions on a real line. Then what would be the complexification of this space? The complexification of this space will be functions of a real argument, but with complex values. Any such a function will have a real part and an imaginary part. So, for example, if we take e to the it then its real part is cos of t, and imaginary part is sine of t. Next, let us give a definition of a Hermitian form. Definition. A Hermitian form on a vector space V over a field of complex numbers is a function from V cross V to complex numbers. So this means that it's again a function on pairs of vectors, and we will again denote it by round brackets, satisfying the following axioms. So one, that U with V1 plus V2 is equal to U with V1 plus U with V2. 2, U1 plus U2 with V is equal to U1 with V plus U2 with V. 3, for any complex scalar C, we have that U with C times V is equal to C times UV. And 4, again, for any complex scalar C times U with V is equal to complex conjugate of C times UV. And 5, when we change the order of vectors, so if we take V with U, then this is equal to U with V and all complex conjugate. We see that the notion of a Hermitian form generalizes the standard Hermitian product on Cn. And in particular, Hermitian forms are sesquilinear. We point out is that for any vector u, we have that the Hermitian form evaluated on UU always assumes a real value. Indeed, by our last property, if we change the order of terms, then we will get UU bar. So this complex number is equal to its complex conjugate, and thus must be real. We give a definition. A Hermitian form is positive definite if for all u in V, u different from 0, the value of the Hermitian form on UU, which is a real number, is greater than 0. Next, let us define the matrix of a Hermitian form. So let B be a basis of V. So let us write B as V1 through Vn. Form matrix A, which is A, B, by setting the entries A, K, S to be the value of the Hermitian form on the basis vectors Vk with Vs. Since the value of Vs with Vk is a complex conjugate of Vk with Vs, we get a relationship that ASK is the complex conjugate of AKS. This gives us the following relationship, that when we take the transpose of the matrix A, then this will be equal to the complex conjugate of the matrix A, where we conjugate every matrix in the entry. Or, so this can also be equivalently written as A is equal to A bar transpose. We give a definition. A square matrix A with complex entries is called self-adjoint. And another term used is hermitian if A is equal to A bar transpose. An example of a self-adjoint matrix will be something like this. 1, 2 plus 3i, 2 minus 3i, and 4. If we take the transpose of this matrix and then conjugate the result, we will get the same matrix A. Let us take a complex matrix A and consider its real and imaginary parts. So let's write it as B plus IC, where B and C are real matrices. Then, if we take this equality, then on the left we will have B plus IC, and on the right, so we have to take B plus IC, then conjugation and transpose. And then when we take the conjugation, so this becomes B minus IC. And when we take the transpose, we get B transpose minus I times C transpose. Now, comparing the real parts and imaginary parts, we get the following lemma. Complex matrix A is self-adjoint if and only if its real part is symmetric So this means that B is equal to B transpose. And its imaginary part is skew symmetric or antisymmetric. That C transpose is equal to minus C. And in particular, for this matrix, we see that indeed it has a symmetric real part and a skew symmetric imaginary part. Next, let us show that a Hermitian form is completely described by its matrix. So we have the following proposition. Let V be a complex finite dimensional vector space with a Hermitian form. And let A or AB be the matrix of this Hermitian form relative to some basis B of vector space V. Then for all U and V in this vector space, the value of the Hermitian form UV may be computed using B coordinates of vectors U and V relative to the basis B. So this will be UB bar transpose times AB times VB. If we compare this with the formula for the bilinear forms on the real space, then the only difference is the conjugation on the first factor. Let's give a proof of this proposition. So let our basis B consists of vectors V1 through Vn, and let us expand vectors U and V relative to this basis. So U is Z1 V1 plus Zn Vn, and V, let it be W1 V1 plus Wn Vn. This means that the coordinate vector of U with respect to B is Z1, Z2, Zn, and the coordinate vector of V relative to the basis B is the vector W1, W2, Wn. And here Zk's and Wk's are complex numbers. Now, let us evaluate the Hermitian form U and V. So if we plug in these expansions, then we get, here we have the sum, k goes from 1 to n, zk vk, with the sum s goes from 1 to n, wk vk. Using the fact that the bilinear form is sesquilinear, then this can be expanded as the sum where k and s go from 1 to n. Here, when we pull out z from the first factor, we pull it out with the complex conjugate. So we get zk bar times ws times the value of the bilinear form on vk with vs. But this is exactly the entry of the matrix A. So this becomes the sum k and s going from 1 to n, zk bar ws times aks. And if we write this summation in a slightly different order, so k and s from 1 to n, and if we write this as zk bar times aks times ws, then we see that this double sum is precisely the matrix vector product. So this is, so we take the conjugate of a transpose of the vector ub times matrix A times the vector vb. And we arrive at our formula. Next, let us show that any symmetric bilinear form on a real space may be extended to a Hermitian form on the complexification of that space. Let V be a real vector space with a symmetric bilinear form. We are going to extend it to the complexification Vc, which is V plus IV, in the following way. If we take a vector in VC with the real part U1 and the imaginary part U2, and take another vector with real part V1 and imaginary part V2, then we define the value on this pair as U1 V1 minus I times U2 V1 plus I times U1 V2 plus V1 V2. And now we have a lemma that I leave it to you as an exercise. This extension is a hermitian form on VC. And the verification of this is straightforward. One has to check that all 5 axioms of the hermitian form will hold. And now let us mention another lemma. Let we have a bilinear form, a symmetric bilinear form on a real space V, which is positive definite. Then its extension to complexification VC is positive definite as a hermitian form. Now, to check this, we just take vector u plus iv, so take a real part and an imaginary part of a vector, and we take it with u plus iv. Then using this formula, this is equal to uu minus I times vu plus I times uv and plus vv. And so here we have a real symmetric bilinear form. So this means that uv and vu is the same. And then the middle terms will cancel, and we get u with u plus v with v. And we see that this is positive if this vector u plus iv is a non-zero vector. Next, we're going to discuss an important application of the theory that we have developed. We're going to talk about Fourier series. Let F be a vector space of piecewise smooth, and we're going to give a precise definition a little later, 2 pi periodic functions. These will be functions from a real line with real values, such that for all x in R, we have a condition of periodicity that f of x plus 2 pi is equal to f of x. An example of such a function could be, for example, f of x is cos of 3x. We note that a 2 pi periodic function is determined by its values on the interval from minus pi to pi, where we exclude minus pi and include pi. Indeed, if we are given a function on the interval from minus pi to pi, then we can replicate this function by periodicity to the whole real line. We see that when we make this replication, we may lose continuity, and because of this, we are considering not smooth functions, but just piecewise smooth functions. We consider a symmetric bilinear form on the space F. Where the value of the bilinear form on two functions f and g is defined as 1 over 2 pi integral from minus pi to pi f of x times g of x dx. And it is easy to see that this expression is bilinear in f and g, and clearly it's also symmetric. It is easy to check that this bilinear form is positive definite. So if we take f with itself, then this is 1 over 2 pi integral from minus pi to pi f squared of x dx. And when we integrate a positive function, then the result is positive. So this is greater than 0 when f is a non-zero function. It will be useful for us to extend this construction into a complex setting, and we consider the complexification of the space F. So here, Fc, which is F plus IF. Now, objects of this space get a real part and an imaginary part. So we can interpret this as functions from a real line to complex numbers that are piecewise smooth and 2 pi periodic. And as we discussed, the bilinear form on F naturally extends to a hermitian form on Fc. So here we get the hermitian form, where the value on two complex valued functions f and g is given by the expression 1 over 2 pi integral from minus pi to pi, and now we take complex conjugate of f times g dx. It is easy to see that this expression gives us a hermitian form, and it is indeed the extension of our earlier formula. Let us make the following crucial observations. That the set of exponential functions, so exponentials of I kx, where k runs over z, so this set is an orthonormal set in our complexified space. Let us recall the Euler's formula. That the complex exponential e to the ikx is defined as cos of kx plus I times sine of kx. So this implies that this function is continuous and 2 pi periodic, and so it belongs to our space Fc. Let us give the proof of this proposition. So we need to calculate the value of the Hermitian form on functions e to the I kx and e to the I mx. So by definition of the Hermitian form, so this is 1 over 2 pi integral from minus pi to pi, and we take e to the I kx with the complex conjugation times e to the I mx dx. Now that becomes 1 over 2 pi integral from minus pi to pi. When we take a complex conjugate of e to the I kx, so here we change the sign of the imaginary part, and what we get is that this will become e to the minus I kx. So we get e to the minus I kx times e to the I mx dx. And now this can be simplified as 1 over 2 pi integral from minus pi to pi e to the I m minus k times x dx. And now we consider 2 cases. So the first case is when m is different from k. So in that case, we can write down the antiderivative of this function. So we get 1 over 2 pi, and the antiderivative is 1 over I times m minus k times the same exponential function, e to the I m minus k x, and this is all taken between x equals pi and x equals minus pi. But this exponential function is periodic. Its value at pi is equal to its value at minus pi. And as a result, here we get 0. Now, in the second case, we consider when m is equal to k. So in that case, so here we're integrating e to the I times 0. So that is 1. And we get 1 over 2 pi integral from minus pi to pi of 1 dx. So when we integrate constant function from minus pi to pi, we get the length of the integration interval times the value of the constant. So this integral is equal to 2 pi, and overall this expression is equal to 1. So summarizing, we get that the value of the Hermitian form between e to the I kx and e to the I mx, so this is equal to 1 if k is equal to m, and it is equal if k is not equal to m, which precisely says that distinct functions are orthogonal to each other, and the length of a single function is equal to 1. So this means that this set is orthonormal. It is natural to ask the question whether this a basis of the space Fc. And well, certainly this set of e to the I kx, where k runs over z, this set is linearly independent. So we proved that any orthogonal set of non-zero vectors is automatically linearly independent. Now, for the definition of a basis, we also need the spanning property. When it comes to the spanning property, there is a difference in how this property is treated in algebra and analysis. In algebra, we require that every vector f in our space is a finite linear combination of basis vectors. And so here, this will be false. For example, any finite linear combination of exponential functions is going to be continuous. So no discontinuous 2π periodic function can be written as a finite linear combination of these functions. In analysis, the requirement is different though, that we want that every f in the space is a convergent infinite linear combination of basis vectors. And we're going to see that this is going to be true. So this set of functions is not a basis in the sense of algebra, but it is a basis of the space in the sense of analysis. Now let us analyze this situation. Suppose we have a function f of x in this space, and we are able to write this as an infinite linear combination of the exponential functions. So we have the sum k goes from minus infinity to plus infinity, some coefficient ck times exponential of I kx. How can we find the coefficients of this linear combination? The trick is the one that we have already seen. So what we do is we look at the value of the hermitian form between a basis function e to the I mx with f of x. And if we substitute for f of x this infinite series, so then we get e to the I mx with the sum k goes from minus infinity to plus infinity, ck e to the I kx. And because we have an orthonormal basis, so e to the I mx will be orthogonal to all terms in this series, except for the case when k is equal to m. And then we see that this is equal to cm. And we obtain the formula for the value of the coefficients in this expansion. Recalling the definition of the Hermitian scalar product, we see that the left-hand side is 1 over 2 pi integral from minus pi to pi e to the I mx complex conjugate times f of x dx. Simplifying this expression, we obtain the formula for Cm. That's 1 over 2 pi integral from minus pi to pi e to the minus I mx times f of x dx. A representation of f as an infinite sum of complex exponentials, so this is called the Fourier series. And the coefficients of these infinite linear combinations are called Fourier coefficients. It remains to make sense of this infinite sum and to understand in which sense do we have equality. Now it's time to give a precise definition of a piecewise smooth function. So a function f is called piecewise smooth if there exist a finite number of points. So x0, which is equal to negative pi, less than x1, less than x2, less than xn, which is equal to pi, such that 1. F has a continuous first derivative in each open interval from xj to xj plus 1, and the second property, that one-sided limits, so the limit when x approaches to xj with a plus of f of x, and the limit when x approaches to xj from the left, all such limits exist and are finite. So this means that the function is not allowed to go to infinity at these points. Here is a typical graph of a piecewise smooth function. And we really do not care what are the values of this function at the discontinuity points. Now we can state the main theorem of Fourier analysis. Let f be a piecewise smooth, complex, valued 2 pi periodic function. Then the Fourier series of f, which is the sum k goes from minus infinity to plus infinity of ck exponential of ikx, where cm is 1 over 2 pi integral from minus pi to pi e to the minus imx times f of x dx. So this series is convergent for every x, and this Fourier series converges to the value of the function f of x for every point where f is continuous and at discontinuity points so when x is equal to xj, Fourier series converges to 1/2 of the left-sided limit x approaches xj from the minus f of x plus right-sided limit x approaches to xj from the right. So the Fourier series does not care how we define the value of the function at discontinuity points, and it always converges to a midpoint between left-sided limit and the right-sided limit. So here it will converge to this point, and here it will converge to this point. And at pi, it will converge to the midpoint between the one-sided limit at pi and at minus pi. So it will be this point here. So ignoring the values of the function at discontinuity points, we can recover all other values of the function from the Fourier series. And we see from this theorem that the Fourier series of a piecewise smooth 2-pi periodic function is convergent. We see that for the treatment of Fourier series, it is very convenient to use complex exponentials. If we want to be confined to a purely real situation, then we will have to use trigonometric functions instead. We have the following proposition. So the following set of 2-pi periodic functions. We take 1, we take cos of kx, and we take sine of kx, where k runs as 1, 2, 3, and so on. So this set is an orthogonal, but not orthonormal set in the space F. I leave the verification of this proposition as an exercise. The bilinear form that we're using here is 1 over 2 pi integral from minus pi to pi f of x times g of x dx. And the values of this form, so for constant function 1, so this will be equal to 1. But for all cosine functions, so if we take cos of kx with itself, then this will be 1/2 for all k, and the same for the sine of kx. And if we take different functions, so for example, cos of 3x with sine of 2x, then the value of this integral will be 0. Let us see now how to expand the function into a trigonometric Fourier series. Let us recall how we do it in finite dimensional spaces. So let v1 through vn be an orthogonal basis of Rn. And we want to find an expansion of a vector u as a linear combination of these basis vectors. Then each coefficient, Cm, is found as a scalar product of Vm with u divided by the value of bilinear form of Vm with Vm. The Fourier series of a function f is going to be a0 times 1, so a constant function, plus the sum k goes from 1 to infinity, ak times cos of kx, plus bk times sine of kx, where the Fourier coefficients are computed using the bilinear form. So a0 is going to be, so we take the bilinear form of a basis function 1 with the function f, and we divide it by bilinear form 1 with 1. All other coefficients ak are obtained as we take bilinear form of cos of kx with f divided by cos of kx with itself. And similarly for bk, so we have sine of kx with f divided by sine of kx with itself. Recalling the definition of the bilinear form, so we get that a0 is 1 over 2 pi integral from minus pi to pi. So 1 times f of x dx, and the denominator here is equal to 1. Then for all other k, ak is equal to 1 over pi integral from minus pi to pi cos of kx times f of x dx. And here these two will cancel because we have 1/2 in the denominator here. And likewise, bk coefficients are equal to 1 over pi integral from minus pi to pi sine of kx times f of x dx. This gives us an expansion of 2 pi periodic piecewise smooth function in a Fourier series, and the Fourier series will be convergent for every x. Let us consider an example. Let's take the following function. F of x is equal to 1 if x is between 0 and pi, and it is minus 1 when x is between minus pi and 0. If we extend this function to the whole real line using 2 pi periodicity, we obtain the following function. And let us point out that functions of this kind often appears as signals in electronics. If we ignore the values of f at discontinuity points, then we see that this function is odd. And this implies that for all values of k, the ak coefficients are all equal to 0, because here the product of an even function with an odd function is odd, and when we integrate an odd function from minus pi to pi, the result is going to be 0. This means that the Fourier series of this function will only have sine terms. So we'll have that f of x is expanded as the sum k goes from 1 to infinity, bk times sine of kx. Let us compute bk coefficients. So bk, by this formula, it's 1 over pi integral from minus pi to pi sine of kx times f of x dx. Now, sine is an odd function and f is an odd function. So this tells us that the product is an even function. And because this function is even, we can compute the integral not from minus pi to pi, but from 0 to pi, and double the result. So we have sine of kx times f of x dx. But when x is between 0 and pi, our function is simply equal to 1. So we get 2 over pi integral from 0 to pi sine of kx dx. The antiderivative here is going to be minus cos of kx divided by k. And we need to take it between x equals pi and x equals 0. This gives us 2 over pi k times negative cos of pi k minus negative cos of 0. So that is 2 over pi k, and here we have 1 minus 1 to the power of k. When k is even, this becomes 0, and when k is odd, the expression in parentheses becomes 2. So what we get is we get 4 over pi k if k is odd, and it becomes 0 if k is even. Now, dropping the even terms, we obtain the following Fourier series, that f of x is equal to 4 over pi sine of x plus 4 over 3 pi sine of 3x plus 4 over 5 pi sine of 5x, and so on. At each continuity point, this Fourier series will converge to the value of the function, that is either to +1 or to -1. And at discontinuity points, it will converge to midpoints between right-sided limit and left-sided limit. So that is, it will converge to 0 at all multiples of pi. Let us evaluate this series at x equals pi over 2. And we note that the value of the function at pi over 2 is equal to 1. And this is a point of continuity of this function. So this means the Fourier series will also converge to 1 by our theorem. Now, if we plug in this value in the Fourier series, then we get the equality that 1 is equal to 4 over pi of sine of pi over 2 plus 4 over 3 pi times sine of 3 pi over 2 plus 4 over 5 pi sine of 5 pi over 2, and so on. Now, the first sine value is +1. The second one is -1. The third one is +1 again, and so these will alternate. And if we multiply both sides by pi, then we get the following equality, that pi is equal to the following series: 4 minus 4/3 plus 4/5 minus 4/7 plus 4/9, and so on. So we see that this Fourier series gives us a remarkable identity for number pi.